Okay. Hi, I'm Chris Kirov, and I'm presenting for Team Mockingbird at the 2022 SIGTYP shared task on cognate prediction. This is joint work with Richard Sproat and Alexander Gutkin, and we're all at Google Research. So linguists have long noticed that words with the same root share similarities across related languages. Published work on these cognate correspondences goes back at least to the establishment of Indo-European by William Jones in 1786, and then subsequent work by the neo-grammarians. The SIGTYP 2022 shared task involves discovering and using these correspondences to recover missing cognate reflexes given a subset of the cognates in neighboring languages. For example, by analogy to the relationship between dream, Traum, and Droom in English, German, and Dutch, respectively, we might expect a system to predict the English cognate corresponding to German Baum and Dutch Boom should be Beam. Beam is in fact cognate with those forms. It's just that it no longer means tree. Its meaning having shifted somewhat to something closer to a plank of wood. For the shared task, we were given cognate datasets from 10 languages for system development. Final evaluations were performed on 10 additional surprise language families. Each dataset consisted of on the order of a few hundred cognates sets, which is actually a very small amount of data. Furthermore, the datasets were ablated, so not every cognate was known. In the most dense condition, 90% of the cognates were present, but in the most sparse condition, only 50% remained available for training. Submitted systems were evaluated based on how well they recovered designated missing cognates. The metrics included standard edit distance, as well as B-cubed F scores, which discount systematic errors, and standard BLEU scores, like the kind you'd see in a machine translation eval. In the end, Team Mockingbird submitted two very different kinds of systems. The first, which we'll refer to as the neighborhood model, is an extension of the transformer architecture, except it encodes multiple inputs in parallel. This model is more complex, but has the advantage, at least in theory, of being able to capture arbitrary contextual cues. The second system, which we'll call the Inpainting model, treats the set of cognates as an image and the missing cognates as corrupted pixels. It borrows a convolutional network approach from computer vision to restore those missing pixels. This model is more simple and trains very quickly on a CPU, but its representational capacity is limited by things like convolutional kernel size. So the plan is to talk about each of the model types in a little more detail, starting here with the neighborhood model. As mentioned before, the idea was to run multiple transformer encoders in parallel for each available cognate. This setup was originally designed to recover the correct readings for Japanese kanji place names based on the readings of their actual geographic neighbors. However, that problem maps very cleanly and directly onto the problem of cognate reconstruction. For the shared task, we submitted 3 neighborhood model variants, which were actually identical, except for the amount of time they were trained for. So we had versions trained for 25K, 35K, or 100K steps. The reason we did this was because we were concerned about the possibility of overtraining given the small amount of data available. And we actually have an open source version of the neighborhood model, which has been released at the Google Research GitHub link below. Here, we can see a visualization of the neighborhood model showing multiple encoders running in parallel. Their outputs are averaged and concatenated, and the result is passed to a decoder transformer that attempts to recover a cognate in a specified language. As noted before, the transformer architecture is large and complex, and the amount of training data available for the task was tiny. So, in addition to varying the number of training steps we used, we took additional measures to mitigate the limited data. We augmented the available data in 2 ways. First, we created 500 different versions of each cognate set by randomly masking out a subset of the available cognates. Second, we created additional neighborhood data by hallucinating new cognates, This was done using a simple unigram pair model. So we counted the IPA symbol correspondences between Levenshtein-aligned pairs of cognates and their neighbors, and we sampled from that distribution of alignments to produce new words. So that's an overview of the neighborhood model. Now I'll switch gears to the inpainting model. So the inpainting model takes direct inspiration from an NVIDIA paper on image pixel restoration. And the convolutional model used in that paper, the convolution operation that is, which is shown in the equation below, is applied in this paper unchanged. Our version of that convolutional network has also been open sourced at the Google Research GitHub link. To apply the model, all available cognates are stacked into an image with IPA characters standing in for the pixels. In the input, some of the pixels are masked out, representing the missing cognates, and it's the job of the model to recover them. So in the end, the model is always producing an image that corresponds to an entire group of cognates. The architecture we used for the model was simple. So there weren't too many character pixels, and each input character was embedded, with masked out characters getting 0 embeddings. That result was run through a single convolution deconvolution layer pair in order to recover character logics at the output for each pixel position. Like for the neighborhood model, we needed to deploy some tricks to deal with the low resource nature of the shared task. We didn't hallucinate cognates, but we did randomly drop cognates from each training group. We also took advantage of the fact that the inpainting model is really small and simple, so we could train it lots of times. For each training set, we created 10 random 80-20 splits into an even smaller training set and a tiny dev set. So we knew that these dev sets would be biased because they were so small, but we hoped that because the splits were random, the bias would always be in a different direction. For each random split, we ran a tuning process using Google's Vizier tool. That's essentially just a smart grid search procedure. Once we had 10 tuned models corresponding to each random split, we did our final inference by ensembling over them just by taking a majority vote. Moving on, the next 2 slides give an overview of how the neighborhood and inpainting models performed compared to the shared task baseline. For brevity, these tables only show the edit distance metric, which should be correlated with the other metrics. Each cell shows results from the most dense data condition, where 90% of the cognates were available, compared with the most sparse data condition, where only 50% were available. There's no need to go through everything, but there's a few key observations. First, as you might expect, there's almost always a very big drop in performance from the dense to the more difficult sparse data condition, where there's very few cognates to train from. If we look at the top row of the table here, which is in green, we see that the inpainting model has the best average overall performance across all the different language families. However, if we look more closely, we'll see that there's actually significant variance across all the language families, with some appearing to be much more difficult than others. Furthermore, there's quite a few individual settings, which are shown in red here, where the neighborhood transformer model actually comes out on top of the inpainting model. In many of these cases, the performance differential is very small, accounting for something like 0.1 average character edits difference. However, there are a few more substantial situations. Like, for example, we can see in red here the situation in the Semitic language family, where the transformer neighborhood model shows a much smaller drop-off in performance when moving from the dense to the sparse condition. Now, this might be because the Semitic language families have fairly complex correspondences between cognates, maybe because of their unique templatic morphology. And it's possible that the neighborhood transformer model is able to capture those complex cues, whereas the simpler convolution-based inpainting model has difficulty representing them. So to conclude, we presented two models for cognate reconstruction, the more complex transformer-based neighborhood model and the simpler but convolution-based inpainting model. Both of these models perform well compared to the shared task baseline. The inpainting model shows the best average performance, but the performance varies across language families, and there's quite a few situations where the transformer neighborhood model actually comes out on top. In the future, resources permitting, it will be interesting to swap low resource strategies between the models. So, for example, it will be interesting to try the inpainting model with the benefit of additional hallucinated data, like we used for the transformer model. At the same time, it will be interesting to try the transformer model with the benefit of additional ensembling, like was used for the inpainting model. And that's the end of the presentation. Thanks for listening. Please take a look at our paper and let us know if you have any questions. Thank you.